Yeah, we've been talking about orthogonality all this while. First of all, we talked about orthogonality, orthogonal sets, orthonormal bases. From there, we talked about the Gram-Schmidt orthogonalization. And in the last video, we had talked about orthogonal projections and least squares. And we see how, the idea of geometry can then is beginning to come into the whole idea of data analysis and all of that, fitting and all of that. So this is the last video on orthogonality, not the last video on linear algebra, by the way. This is the last video on orthogonality, and we'll be talking about some applications of orthogonality, which we have seen already, but for the sake of emphasis, I want to talk about that. Okay. So of course, we see some key applications of orthogonality will be in data fitting and signal approximation. And by way of introduction, orthogonality is a fundamental concept in linear algebra and functional analysis. It allows us to find best approximations. The broad subcategory of these four videos I've been doing on orthogonality has been orthogonality and approximations. So the idea of least square is some kind of approximation, right? So and that is what we brought into data fitting. So orthogonality is a fundamental concept in linear algebra and functional analysis. It allows us to find best approximations, minimize errors, decompose complicated data signals, and project vectors and functions onto simpler spaces. All right. So the main principle here is that the best approximation of a vector or function lies in the direction of its orthogonal projection. So that's fundamental. And that's this whole thing now is what you can project into natural language processing. When you talk about cosine similarity and everything, it's basically the same concept that the best approximation of a vector or function lies in the direction of its orthogonal projection. So let's see data fitting using orthogonality. Um, the data fitting problem, suppose we have data points x1, y1, x2, y2, up to x and yn. We want to find a function y which approximates f of x. And we have common models like a linear model, like what we saw the other time in the last video about least squares, y equals ax plus b, quadratic, y equals ax squared plus bx plus c, polynomial, y is a naught plus a1x plus all of that up to ak x raised power k. Usually, no exact fit exists, so we minimize the error. So anyone you use, there's going to be error, but so we just try to minimize the error. So we talked about the least square principle in the last video, where we saw that we could say that y I cap is something like f of xi, and the error point I, error at point I will now be ei equals yi minus yi cap. So this is the EI. So total squared error then will be E equals summation from I equals 1 to n of yi minus yi cap all squared. So the least squares method chooses parameters that minimize E. So we want to minimize the error as much as possible. So for vector interpretation, how does that go? So we write the system as AC, which is approximately where. That was exactly what we did in the last video where we said AX is approximately B, the right-hand side. So same thing. So where A is the data matrix now. So you have data and, you form a matrix with that. And C is the coefficient vector. Maybe we are looking for the AB I found in the last video, for instance, is the coefficient vector. And why is the data vector? So like when you have pairs of that time we had, I think, 1, 2, 2, 3, and 3, 5, right? So all the 1, 2, 3 are the data matrix, while the C, the coefficient vector, maybe the A and B we're looking for, and Y is 2, 3, 5 that we are also looking for. But then in that case, now we need to now make up matrix A, we make it up with 1, 1, 1 by the other side, like that. So, okay, I mean, this is what exactly I just talked about now. So, example for linear fit now, all the x1, x2 up to xn, you augment with 1, 1, 1 like this, all right, to make it compatible for multiplication. So C now is AB that you're looking for all the fitting. So like as you can see for all the fit here, we need all this AB kind of stuff, ABC and so on and so forth. Um, and then we have orthogonality condition. So the best approximation satisfies A transpose into AC minus Y equals 0. Of course, that was the same thing like A transpose into AX minus B equals 0. And it is from here we got, this means that the error vector is orthogonal to the column space of A. So the error vector AC minus Y is orthogonal to the column vector of A. To the column space of A rather. So this leads to the normal equations where you now have A transpose AC, minus A transpose Y, which is now A transpose AC equals A transpose Y. Or in the other video, we said A transpose AX equals A transpose B. So to get X now, you need to take the inverse of A transpose A. And that's why A transpose A inverse multiplied by A transpose Y or A transpose B would give you C, or what we called X in the last video. And I even made some examples with that. Okay. Oh, this is exactly what I did the other time. So thankfully, I won't have to do that again. Okay. So in this case, this is exactly what we did in that video. So where we had these point pairs, for x1, x2, x3, 1, 2, 3, y1, y2, y3, 2, 3, 5. So we can now fit that to y equals ax plus b. So we form the matrix A. That's the x1, x2, x3 with 1, 1, 1 by this side. And then on the right hand side, we have this 2, 3, 5, which we called B the other time. I think this is even better so that we don't confuse that with A and B that we have here. So I did that in the last video. So if you want to check that, exactly the same thing. So if you do A transpose A, that's like this 3 by 2 matrix becomes a 3 by 2 matrix when you transpose it. So it now becomes 1, 2, 3, 1, 2, 3, 1, 1, 1, like that. So that'll be 1, 1, 2, 1, 3, 1, like that. And this, so if you do that, if you do A transpose A, you get 14663 that we did the other time. I guess I can still even flash it here. I think do I still have that here? I think so. Yeah, this is it right here. So I can just show you all of that. So, just like you have 1, 2, 2, 3, 3, 5, it's exactly the same thing when you have X, Y. So you have 1, 2, 2, 3, 3, 5, like that. And then we went ahead to have, so A is this, B is that. In this case, now we now call this is what we call Y now, all right? This is what we call Y now. And then this is what we have come to call C. And then this becomes the Y, like this. And then for A transpose A, so this is what I meant. So row 1, 1, 1 becomes 1, 1 column. Row 2, 2, 1 becomes second column here. 3, 1 here becomes third column here. All right. And then you multiply the two together. So, and then this gives you 14663. And for A transpose B, now we said B should be Y, right? That's A transpose Y. So Y is 235 as you have it here. So A is 112131. So if you do all that, you end up getting 23 by 10. So now this is Y, right? So A transpose Y. So then we need this C, A transpose C, and this is Y. Okay, so now that C now is AB that we need to do the fitting. And you see, to get this AB, we need to take the inverse of this one. So, and the inverse, if you take the inverse of this cancels this, so it comes over to this side. And for a 2 by 2 matrix, the inverse is very simple from what we've done previously. Just take the determinant, 14 times 3 minus 6 times 6. So 1 over 14 times 3 minus 6 times 6. Then for this, you reverse 14, 3 comes here, 14 comes here. And then you change the sign for this one. So 6, 6 becomes minus 6, minus 6. So then you can just then, take this determinant. You have 1 over 42. 14 times 3 is 42 minus 36. Then you have 3 minus 6, 14. Then, of course, you can then go ahead and multiply these two together. So, and that's because this is two rows, you write this two times 23, 23, 23, 10, 23, 10, and then you have 3 minus 6 over the top, minus 6 over 14 over the bottom, and then you then have 23 times 3, 69 minus 60, 23 minus 6, 138 plus 140, and then you have 1 over 6 into 69 minus 60 is 9, 138 plus 140 is 2. So you have 9 over 6, 2 over 6, and then you get those values, and then you get your results, which is now like y equals 1.5x if you like, plus 1 over 3 or 0.667 if you like that. So exactly the same thing we did in that other video. So, and that's how we get this fitting right here. So the question now is, what is the meaning of orthogonality? So let the error between y and, we want to approximate AC with to y. So, but there's going to be a difference. So the error in y minus AC then is that the error is perpendicular to the column space of A, right? So this means approximation is a projection and error is perpendicular and distance is minimized, right? So, apart from that data fitting, we also another application of orthogonality is signal approximation using Fourier series. So interesting, I have a whole playlist on what is that thing called now? Mm, Spectral analysis. So that I dealt a lot with signals and all that. So signal approximation using Fourier series. Signal approximation problem. So here, let f of x be a periodic function on closed interval minus pi to pi. We want to approximate it using sine nx and cos nx. So these functions are orthogonal. So sine nx and cos nx are orthogonal. So you see orthogonality coming into trigonometry here too. Okay. So orthogonality of trigonometric functions tells us that on this closed interval minus pi to pi, the integral from minus pi to pi of sine mx sine nx dx is equal to 0. For m not equal to n, then cos mx cos nx dx is equal to 0 also from m not equal to n. Then sine mx cos nx dx is also equal to 0 over the same interval. So anyhow you look at it, except that here, for any m and n, it's always the case. Therefore, we can say that sines and cosines form an orthogonal basis. Sine and cosine form an orthogonal basis. So then that takes us to the idea of Fourier representation. So a function can be written in Fourier form. I have a playlist of Fourier series, so you want to check that out if possible. So a function can be written as f of x equals a naught over 2 plus summation from n equals 1 to infinity of an cos nx plus bn sin nx, where an is all this, bn is all that for Fourier. And then we can talk about projection interpretation. So you see how all of that is playing into the idea of projection. So each coefficient is a projection now. So for instance, that an you have is actually a projection, which is this f cos nx all over cos nx cos comma cos nx. Bn is for sine now. So this is similar to vector projection where we said if you the projection of v onto u will be something like v dot u over u dot u multiplied by u. That's the projection of v onto the vector u. So the Fourier series of f of x equals x, for instance, as an example. So let f of x be equal to x on that closed interval minus pi to pi. This is an odd function, right? This is an odd function. So that so odd function means that the idea of odd function is that uh, for for an odd function, okay, f of minus x is equal to minus f of x. That's what an odd function is simply about. For even function, on the other hand, even function, for even function, right? F of minus x is simply the same thing as f of x. So a very good example of odd function, like we said here. So example for this is f of x equals x as a good example. So because minus 1 f of minus 1 is minus 1, right? So another one will be for trig. Now that will be sine x. Okay. So sine minus 30 is minus sine 30, right? But here, f of x, if f of x equals x squared is an even function because f of minus 2 is the same thing as uh is the same thing as f of 2. So here f of minus x is equal to f of x. So here f of minus 2 is so if you put 2 you get 4. If you put minus 2 you still get 4. The other one, f of x equals cos x, is an even function on this other hand. So that's the deal here. That's the kind of idea we're working with. So because it's an odd function, now therefore all our an to be equal to 0. So the kind of an you have here is just 0 straight up. That makes life a bit easy somewhat. So in that case now, only sine terms remain. So because all the cos components are gone, so f of x is now summation, see what you have originally, right? So because all the ans are gone, so only sine remains because bn will not be 0. So and then we have only sine terms remaining. And as a result of that, f of x is summation from n equals 1 to infinity of bn sine nx. We compute bn as to be 1 over pi integral from minus pi to pi of x sine nx dx. Using integration by parts, we end up getting bn. If you want more detail on this, you can check my playlist of Fourier series, which I did into some detail. So bn is now 2 into minus 1 raised by n plus 1 over n. And the final result is x equals 2 summation from n equals 1 to infinity of minus 1 raised by n plus 1 over n sine nx. Okay, so that's a very good example of how, orthogonality plays into this as sine and cosine are orthogonal. Then we have another example about sine a square wave, right? If you define f of x to be 1 for x between 0 and pi and minus 1 for x between minus pi and 0, this function is odd, right? So in that case now, we only have the an part will also go to zero as just like before. So f of x is summation for bn sine nx. So the coefficient now bn is now 4 over n pi for odd n, and bn is 0 for even n. So Fourier series, so for all the even parts now, that's why you don't see any even thing here. So all the sine 2x and 4x are gone because bn is 0. So Fourier series for this square wave now will be 4 over pi into sine x plus sine 3x plus 1 over 5 sine 5x plus 1 over 7 sine 7x and so on and so forth. Okay. Then we talk about the best approximation property. So let Sn of x be a naught over 2 plus summation from n equals 1 to n of an cos nx plus bn sin nx. Then Sn minimizes integral from minus pi to pi of f minus Sn squared dx. It is the best mean square approximation. So you have mean square approximation coming here. So the unified view of orthogonality we see here is that both data fitting and signal approximation use projections. So the context, so look at the context, the space, the basis, and method. For data fitting, you talk about n-dimensional real number system. For the basis, you talk about columns of A, and for the method, you talk about least squares. Then in the context of signals, the space is function space, and the basis you talk about sine and cosine, and for the method you have Fourier series. In both cases, you discover that these approximations are basically projections where errors are perpendicular to the subspace, right? So where errors are perpendicular to the subspaces, better still. So general projection formula in that case, you have let this collection, the set of all V1, V2 up to VK be orthogonal vectors. So projection of U onto their span, projection of U onto V, just the summation from I equals 1 to K of U comma V1. That's U dot VI, all over VI dot VI times VI like that. So you do it for all the possibilities. And then this applies to vectors in n-dimensional space and functions in Fourier series altogether. In summary, we see key ideas like data fitting, which uses least squares, solves normal equations, error is orthogonal, and produces best fit. So, and we also have for signal approximation, which uses Fourier series and uses orthogonal functions because sine and cosine are orthogonal, coefficients are projections, and gives best mean square fit. So the main principle we see here is that orthogonality allows us to project complicated objects onto simpler spaces with minimum error. Okay, orthogonality allows us to project complicated objects onto simpler spaces with minimal error. So we have some practice problems here that you can try your hands on. So solve all questions fully, showing you're working. Given the data 1, 1, 2, 2, 3 to find the least squares line. So just like what we did before. So you just have A to be 1, 2, 3 against 1, 1, 1, whereas Y now is 1, 2, 2, and then you do all that fitting. So you can also do something quadratic too. This is going to be more engaging because you need to look for A, B, and C. So it's going to be more serious. So never mind. You can just, okay, I think I want this to be proper, as I always like to do. So here I have dollar backslash math bb, this and that. And then voila. Let me copy this in case I need it next time. Okay, so that looks more beautiful than what it currently is. So you see it's R3 now. So projection in R3, we have 2, 1, 3, 1, 0, 1, 0, 1, 1. Find the projection of U onto the subspace spanned by V1 and V2. So in this case now you do that U onto V1, U onto V2. And for U onto V1, right, that'll just be U dot V1 over V1 dot V1 times V1. And the U onto V2, that's U dot V2 all over V2 dot V2, right, times v2 multiplied by v2, right? Then for orthogonality check, show that the vectors v1 and v2 are orthogonal. Of course, 1 times 2, 2, 2 times minus 1, minus 2, minus 1 times 0, 0. So 2 minus 2, 0. That's orthogonality. Then find the projection of 3, 1, 2 on 2, v1. So that will just be u times v1 all over v1 dot u dot v1 all over v1 dot v1 multiplied by v1, right? So that's how that goes. So best approximation in R2. Okay, this is the kind of thing I knew I was gonna see most likely. So just put this right here and then close up this with the dollar sign, and we have that again. So I come back and see it's looking beautiful. Okay, let it U be 4, 3 and V be 1 to find the best approximation of U in the direction of V. Okay, so I think that's going to be the projection thing like that. So Fourier series of an even function. You can also try this. You can use symmetry in this case. Then Fourier sine series. Find the Fourier series of this. So, like I said, you can check my playlist on Fourier series to clarify this whole thing, right? So here we have least squares matrix problem. You have A to be this and Y to be that. Find the least square solution of AC equals Y. So here now you need to find A transpose A, and then the inverse of that you multiply by A transpose Y, right? And then that can help you to find this is so then you find the error vector, verify that the error is orthogonal to the columns of A and all that. So with this, I come to the end of this interesting video about applications of orthogonality, right? And we see that the application we can have it for data fitting and signal processing, if you like. So let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. Don't forget to try your hands on the practice problems. That's the way to verify if you really understand the concepts. If you have subscribed already, I must thank you very much for doing that. If you haven't subscribed, the question is, what are you waiting for? Go ahead, subscribe, hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of the channel by clicking on join, right? By clicking on join, you can actually become a member. And then that gives you some special privileges that you're going to see, like, some videos only you will see them. Some videos you see them first before other people. Um, you can request for my PDF notes. We can hang out together to discuss anything that interests you on my channel, be it mathematics or data analysis or data science, machine learning, scholarships, writing books, anything that interests you at all on my channel. We can discuss all of these things. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.